This is the second section in the elastic collisions in 2-dimension, and this is successive oblique impacts. So all this is there are multiple collisions, probably 2 at most, and if it's talking about further collisions, there's going to be some sort of pattern where we can predict what's going to happen, like in a third collision, because it follows some sort of pattern or sequence. But like it'll be like 2 collisions. So the way that we deal with these questions is, you've got to deal with the first collision first. Once you've worked out what's gone with the first collision, then that will tell you what's going on at the beginning of the second collision. Yeah, so do each part separately. Make sure you keep a clear record of your steps. Make sure that you use exact values, use your calculator as you go on. Don't round like halfway through a collision after the first collision. Don't use your rounded answers. Use your exact answers. Get used to using the memory button on your calculator or the answer button so you get those exact answers. Okay, 2 vertical walls meet at right angles. A smooth sphere slides across a smooth horizontal floor, bouncing off each wall in turn. Just before the first impact, the sphere is moving with 4 meters per second at an angle of 30 degrees to the wall. The coefficient of restitution between the sphere and the walls is 3/4. Find the direction and motion, direction of motion, speed of the sphere after the first collision. So it's really important that we get a clear diagram of what's going on. So let's start by drawing 2 walls that meet at right angles like this. Yeah, so here's our 2 walls. It says that the smooth sphere slides across a smooth horizontal floor, bouncing off each wall in turn. So it's almost as if we're looking at this from above. Just before the first impact, the sphere is moving with speed 4 meters per second and an angle of 30 degrees to the wall. Okay, so we're going to have something like this. Yeah, where this is 30 degrees. And then it's going to bounce off there, and then it's going to then bounce onto that wall and then bounce off again like this. So this is just a sketch, so don't think, all right, these are right angles, it must definitely be this particular angle. It's only a sketch, and we've got the speed here as 4 meters per second. So we're going to call this V and this angle here beta. So we're now ready to start part A, and the direction of motion and speed of the sphere after the first collision. So we'll need to write on and work out the components. So rather than draw on the diagram, I'll actually write out parallel to first wall. Okay, so I'll call this the first wall, and this one the second wall here. So if I look at what's going on parallel to the first wall, then I will have, actually I think I will draw it on, it does make it easier to see what's going on. So there and that, so these components here, so parallel to the wall, that's going to be 4 cos 30, and this will be 4 sine 30, and then over here this will be V cos beta, and this will be V sine beta. So yeah, actually drawing on the diagram does make it easier. So parallel to the first wall, there's going to be no change in those velocities, so we get the equation that 4 cos 30 equals V cos beta. Now cos 30, should know this off by heart, root 3 over 2 times by 4 is 2 root 3. So that gives us v cos beta equals 2 root 3. Now perpendicular to the first wall, so perpendicular to first wall, the coefficient of restitution is 3/4. So I have 3/4 equals, now the speed that it rebounds from the wall, or the velocity, is v sine beta. And the approach, you can't see it very well, but it's actually 4 sine 30. 4 sine 30. And we can then cross multiply. That's one thing we can do. So I'll have 12 sine 30 equals 4v sine beta. So rearranging that, I will get v sine beta equal to, well, I'm just dividing both sides by 4, so that'll be 3 sine 30, and 3 times sine 30 will be 3/2. Right, so let's just take stock of what we've done. I've used the parallel and perpendicular components to come up with these two equations. I'm trying to find the direction and the speed, so I need to find beta and I need to find v. So now I'm going to solve these two equations simultaneously. So for example, I could do v sine beta over v cos beta. That gives me tan cos beta, and that will equal 3/2 over 2 root 3. So from that I will get tan beta equals, so let's work out what this gives us. That's root 3/4. So tan inverse of that will give us beta. Let's do that. Tan inverse will give us 23.4 degrees. That's 3 significant figures, 1 decimal place. And we're going to use the exact value to work out what v is. So I could, for example, substitute that into any equation really. Let's substitute it into the sine equation now that we have beta. So v equals, it's going to be 3/2 divided by sine beta, okay, which is basically going to be that. I'm going to use the answer button. So we'll have 3/2 1.5 divided by sine, and I'm just going to press the answer button, and then I get 3.7, 3 significant figures, 3.77 meters per second. So we have our angle beta, let's just highlight it, and we have the velocity there. Okay, now I'm going to try and keep hold of those, because in part B it tells me I want the direction of motion and the speed after the second collision. Right, so part B. So we now need to know what this angle is here. This is going to be like the angle that it approaches. We know V. Now, since we know this angle is what, 23.4, this angle up here is going to be, because it's a right angle triangle, it's going to be 90 minus 23.4. Now I'm going to be trying to use exact values as much as I can. So this angle here is basically 90 minus 23.4, put dot 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 because that was rounded, and this velocity, this approach velocity here at 3.77, and again I'll put ... because that was rounded to 3 significant figures, and basically we carry out the whole process again. So I'm going to mark on my diagram now the second set of velocity. We're going to call this one W, and this angle here, we'll call that gamma. Why not just keep going through the Greek alphabet? And so this is our second wall. So what we want is these components here. So this one, these two are going to be equal, and it's going to be this component here, which we need to work out, and that is going to be W sine gamma, and this bit here will be W cos gamma. So 2 equations just like before, parallel and perpendicular to the second wall. So if we do parallel to second wall, that will be our V sine beta, which actually is 3/2, will equal W cos gamma. So V sine beta equals W cos gamma, and we know from the previous bit we did that V sine beta equals 3/2, so that means that W cos gamma equals 3/2. So there's our first equation. Just like before, we're now going to be looking at perpendicular to the second wall. So perpendicular to second wall. So using the coefficient of restitution, which is 3/4, we've got the rebound as W sine gamma over the approach, which is 3 cos beta, or V cos beta equals 3/4. So what we can do from there is we can cross multiply, and we'll have 4 W sine gamma equals 3V cos beta. Now what we can do from there, because we actually know, well actually let's just highlight this, we know V and beta. So now I'm going to do sine gamma, or W sine gamma over W cos gamma. So that'll be my next step. So W sine gamma over W cos gamma. Yep, so this is where I'll end up with tan gamma. So I can do the tan inverse. So sine gamma, well, I can take this and just divide it by 4 to get W sine gamma. So it'll be 3/4 V cos beta at the top. So 3/4 V cos beta divided by W cos gamma. Well, that's just 3/2. It's just there, isn't it? So that's 3/2. 3/2. So I want to try and be as exact as possible. So the top part, that tan gamma, that'd be 3/4 times by V. So 3/4 times by V. Now V was 3.77, so I'll just put ... there, times by cos beta. Now beta we rounded to 23.4, so I'm going to try and use the exact answer over there. all divided by 3/2. So I'm going to try and be exact as I can using the memory and work out what gamma is. Now I use the memories, so like shift and STO to recall values and STO to store values, and I stored those values for V and beta in memories A and B, and doing that gave me exactly 60 degrees. Now I think if you use the rounded values, you'll get like 60.01 or something like that, but the exact values actually ended up giving me an exact value for that angle. So I now know the direction of motion. The next thing I need to do is to take that value of gamma and substitute it into an equation. Let's substitute it into this equation here. The W cos gamma equals 3/2. So now I can work out W. So W will be 3/2 divided by cos 60. So we'll just do that now. So last step, W, so using this equation here, W equals 3/2 divided by cos, and it's exactly 60 gamma. And let's see what we get. We should get a nice answer hopefully. So 3/2 divided by cos 60, and we get exactly 3. So it's 3 meters per second. So for the second bit of the question, we can say that the angle is 60 degrees and the speed is 3 meters per second. So there's our answer for the second bit. So here we've got this second collision, and we try to be as exact as we can. Okay, two cushions of a snooker table, W1 and W2, meet together at right angles. So very similar to the last one, not walls, but cushions of a snooker table. They meet at right angles, as it should do if it's a proper snooker table. Like this. So these are two corners of the snooker table. Let's put the little pocket there in the corner where the ball's going to go, like that. And a snooker ball travels across the table and collides with W1 then W2. So let's call this one W1 and we'll call this one W2. The cushions and models are smooth, so there's no friction. Just before the first impact, the ball is moving with speed u meters per second, so it's going like that, and u meters per second at an angle of 20 degrees to W1, so this is 20 degrees here, like that. The coefficients of restitution between the ball and the cushions, W1, W2 are a half, so this is a half. The coefficient of restitution for this is 2/5. Now I would have thought they would have been the same for a snooker table, but never mind. Find the percentage of the ball's original kinetic energy lost in the collision. So what's going to happen is this is going to collide, and then sort of go off something like that. So let's now put in all the components of these different speeds here. So we have u sine 20 here. Down at the bottom here we will have u cos 20. If we call this velocity v and this one w, and we call this angle here alpha, then this angle here is going to be 90 minus alpha, and we'll call this angle here beta. So again, we can put these components in. So this bit here is going to be v cos alpha. This bit here, so we're using the angle alpha, actually it makes things a bit easier. This will be v sine alpha, And then if we move to the last part in a nice red, dark red colour, we'll have this component here, which will be W cos beta, and then we're left with this component here. We'll just write down what that is. That will be W sine beta. So we've got all these different components now which we can use to solve the question. Now the amount of kinetic energy that's lost, so Ke lost, is going to equal the amount of kinetic energy, I suppose if we do it the V way, so we'll get a negative answer. So half m v squared, that will be the final velocity at the end, which is going to be w. Okay, so there's our final velocity there, minus half m u squared, because that will be the velocity at the start. So minus half m u squared. So that will give me the kinetic energy lost. Right, it's going to be a lot of algebra in this. So let's start with W1 and see what's going on with W1. So we will look at the velocities parallel, which is going to be u cos 20 equals v cos alpha. Then if we look at what's going on perpendicular to the to W1, so we've got our speed of rebound, which is v sine alpha, over the speed of approach, which is u sine 20, equals e, which is going to be a half. Now I basically want to eliminate u from the equation because I want v and alpha, that I can then use those to work out beta and w. So if I take this equation and I'll say u equals v cos alpha over cos 20, okay, I can substitute that for u in here, and that will give me the equation where I've eliminated u. So I will have v sine alpha over u, which is v cos alpha over cos 20 times by sine 20. That equals a half. So from there, what will happen is the sine 20 over cos 20 will become tan 20, and I've also got well, the v's will cancel out, so let's cross those out, and then I'll also have sine alpha over cos alpha, so that will become tan alpha. So simplifying that out, what I'll end up with, well actually let's do it in two steps. So sine alpha over cos alpha, and actually that's going to be over tan alpha, so I'll put times 1 over, sorry, tan 20, that equals a half. So we have basically tan alpha over tan 20 equals a half. So then we will have tan alpha, or 2 tan alpha, tan alpha, it will be 2 tan alpha equals tan 20, so divide by 2, I will end up tan alpha equals a half tan 20. So now I've got an expression to find alpha, which I can then use in the next part of the question. Right, so now we're going to look at W2, and then we're going to use this in W2. So what's going on with W2? So again, we look at what's going on parallel to W2 and what's going on perpendicular to W2. So parallel to W2, V sine alpha equals, I think that's W cos beta. W cos beta. Then if I look at what's going on perpendicular to W2, so the rebound is W sine beta over the approach, which is V cos alpha. V cos alpha. That's going to equal the coefficient of restitution for W2, which is 2/5. So next step, I'm going to take this, cross multiply, and I will have 5 W sine beta equals 2 V cos alpha. And now I'm going to use the V sine alpha and V cos alpha to get tan alpha. Reason being, I've got tan alpha equals something. So here, I'm going to take and actually write it as, down here, V sine alpha over V cos alpha. Okay, well that's just tan alpha, isn't it? And tan alpha, based on what I've got here, so that's going to be W cos beta. So W cos beta, rapidly running out of space here, over V cos alpha. So V cos alpha from this is basically, just divide that by 2, so 5 over 2 W sine beta. So 5 over 2 W cos, not cos, sine beta. So what happens? Well, the W's cancel out. And basically that's the same as cot beta. So I could actually write that, couldn't I, as dividing by 5 over 2 is the same as 2/5. So that's 2/5 cot beta. Now what does that equal? That equals tan alpha. And tan alpha, well, I'll work that out from here. That's this. So half tan 20. I told you lots of algebra. Half tan 20. And from here we can work out what beta is, can't we? Yeah. So we can do the reciprocal of both sides. And basically beta is going to equal, so I'm actually going to just do lots of working in one step. Actually, let me write down what tan beta is, that might be a bit easier. So tan beta, so once I've done a reciprocal of both sides, is going to be 2 over 5 times half tan 20. So you might want to pause it and have a look, because I've missed out a few steps of working, but it's the type of thing you should be able to fairly easily do in your head. So I've done a reciprocal of both sides to change the cot to tan, and basically then divided both sides by what would be 5 over 2 when we've done the reciprocal of that, or times by 2/5. So from there we'll get a value of beta as, and I think I've worked out on my calculator, got it down here, yeah, 65.536 degrees. So we'll call that 65.5 degrees, 3 significant figures, 1 decimal place for that angle beta. So now we've got that angle, we can use that angle, so I'm going to have to go all the way up here to try and finish this off due to a lack of space once again. So I've got my value of beta. I can put that into an equation that will enable me to find W. So I will use this equation here. So again, this is one of these questions where I don't know U, but we're told that it starts with speed U. So my answer is going to be in terms of U. So I'm trying to find W. So W will equal V cos alpha over cos beta. So I'll write that down. So W equals V sine alpha over cos beta. Now we'll start with the bottom part because we know that. So cos beta is going to be cos of this 65.5 degrees that I worked out down here. So dots to show that it's not exact. And the bit at the top, I can use another equation to get V sine alpha, and that's this equation here in terms of U. So if I cross multiply, I will have here that V sine alpha, or 2V sine alpha, equals U cos 20. So 2 of those equals 1 of those. So if I want V sine alpha, it's going to be half of this. Yeah, so half U sine 20. So I'll write that down. So half U sine 20. I'm really scrabbling for space here. So we can work that out for W. It's going to be in terms of U. So it's going to be something U. So it's basically half sine 20 divided by the cosine of my answer, that's 65.5 degrees, and I get 0.41295 U. So we want to go for 3 significant figures. So W is going to be 0.413 U. So I suppose I put 3 significant figures. I'm not quite finished yet, have I? So I've got this angle at which it of the second rebound. I've got the speed of the second rebound. Okay, so what was I using that for? Well, I'll go back to the original question, which was to work out the kinetic energy lost and the mass of the snooker ball. Well, we're working out the percentage loss, so actually the mass doesn't matter, that's going to cancel out. So to find a percentage lost, what we want is the change in the kinetic energy divided by the original amount of kinetic energy. Right, so the change in kinetic energy is the kinetic energy we had before minus kinetic energy we had at the end. So we started with half m u squared, and then it dropped down to half m, and then this value of w here, so that's the kinetic energy or the speed afterwards. So it's going to be this 0.413 u all squared divided by the original amount of kinetic energy, which is half m u squared. Now what happens is the halves cancel out, the m's cancel out, and actually when we expand the brackets, what we will have is this squared and u squared, so the u squareds cancel out. So all we're left with after all of that is just 1 minus this 0.413 squared. Now when we do that, we'll get 0.8294 0.47 dot dot dot. So we need to change that to a percentage. So that would be 82.9% of energy loss. So we finally got there for the final answer. Lots to do there, lots of algebra. But the final answer is 82.9% of energy lost, or 83%. And then part B, we're going to have to create a bit of space to do part B. In reality, the cushions may not be smooth. What effect will this have, will the model have on the calculation on a percentage of kinetic energy remaining? Well, if they're not smooth and they're rough, we're going to lose energy because of work done against friction. So the percentage of the kinetic energy remaining is going to be lower. Okay, so let's answer that. So part B, so work will be done against friction okay, which will mean more KE is used, so less KE will be remaining at the end. Right, so just like before, we've got a view from above. Two smooth vertical walls stand on a smooth horizontal surface, and they intersect at an angle of 60 degrees. So here's my first wall, then an angle of 60 degrees up here for the second wall, and it says that the sphere is projected across this smooth surface at an angle of 20 degrees, so something like that maybe, a speed of 1 meter per second, an angle of 20 degrees, and I need to work out what's going on after the first collision. So it's going to be going off like this. Now I may change this angle because that may help me work out which direction it's going to go in after the second bounce, because at the moment what I don't know is when it does this, I don't know whether it's going to go off in this direction or this direction. That's going to be important. So if I can get some sort of idea and get this sort of roughly right, it's going to help me work out which direction it should go in afterwards. Anyway, let's work out what's going on in the first collision. So for the first collision, we want the two components there, here, here, and here. Yeah. So we will call this V, and we will call this angle alpha. So first equation, if we look at what's going on parallel to the first wall, so we'll have 1 cos 20 or cos 20. Here we will have V cos alpha. Here we'll have 1 sin 20 or just sin 20. And over here, that's going to be V sin alpha. So our two equations are going to be, first one, parallel to the wall, cos 20 equals V cos alpha. Perpendicular to the wall, we will have V sin alpha over sin 20 equals the coefficient of restitution. I didn't write that down, did I? Which was 0.4. Right, if I rearrange this, I'll have V sin alpha equals 0.4 sin 20. So now I can do V sin alpha over V cos alpha to get tan alpha, and tan alpha will be equal to V sine 20, which is 0.4 sine 20 over V cos alpha, which is cos 20. So doing the tan inverse of that, whoops, the tan inverse of that will give me alpha. So I'll do that. So quickly, tan inverse, and I'll just plug it all in, of fraction button 0.4 sine 20. I suppose I could have simplified it out, but never mind. And I get three significant figures, 8.28, and it goes 3385902. So I'll call that 8.28 to three significant figures. And now we want to work out what the, so that's the angle. We now need to work out the speed. We've got the direction and the speed. We can substitute that 8.28 into any of the equations now. So let's substitute it into this one here. Yeah, let's put that down here. So rearranging it and putting that in, we will get V equals cos 20 divided by cos, and that's our 8.28. I'll use the answer button. So cos 20 divided by cos answer, and I get to three significant figures. V equals 0.49599, so 0.950. Okay, so let's just highlight that before we move on to the next part of the question. So there's our answers there for part A, and we'll move on now to part B, not in yellow but in black. We will move on to part B. Now I did say before I wanted to maybe adjust my diagram based on this angle alpha, so that's going to help me decide where this is bouncing afterwards. So let's just take these off for a minute. So we'll take those off, and now we'll just look at the second part of what's going on. Obviously in the exam you just draw a fresh diagram for the next part. Now I had the angle that it bounced off, so it's bounced here at 20 degrees and it bounced off at only 8 degrees, so it's very, very shallow. So it's actually bouncing sort of something like this, which actually means when it bounces off it's going to bounce back, it looks like it's going to bounce back this way. Now if I don't get it right, I will just get a negative for my answer. So here, this angle here, which I'll call beta, that's the angle that I will need to find. I've worked out V, so this is 0.950. I've got this angle here, that's my 8.28 degrees to three significant figures. And we'll call this W here, let's use a different colour, and this is the angle that I want to find here. And actually beta, I'll take that out because beta I can work out, but this angle here I'll call that beta. So if I zoom in on this diagram here, so I can work out this angle here. Let me just draw the triangle down at the bottom. So what I've got at the moment is, this is 60 degrees, this is 8.28 degrees. So I can work out this angle here, by doing 180 minus 60 minus 8.28, and that gave me 111.72, which means this angle here, because it's on the straight line, is 68.28 degrees, the sum of the other two. Right, so let's put that in. 68.28. That's not very nice, like that. Let's stick it outside. 68.28 degrees. So just like before, we're going to be looking at the horizontal and vertical components. So let me just turn the diagram around and draw it like this. So we've got basically it's, this is sort of exaggerated, the way I'm going to be drawing it, so none of this is to scale here. So it's something like this going on, where this is 0.950. This angle we worked out here is 68.28, and we're calling this angle beta, and we'll call this W. So let's put our components on here. Oops, wrong way. Got to get the direction right. So here, here, one here, one here. So I'm actually going to write them on before I write the equations. So 0.95 cos 68.28. Here 0.95 sine 68.28, and then W cos beta and W sine beta. So let's look at what's going on parallel to this second wall. So parallel to the wall, we're going to have W cos beta equals 0.95 cos 68.28, and perpendicular, the speed of rebound is going to be W sine beta equals, not equals, using the coefficient of restitution, so that's speed of rebound, speed of approach, 0.95 sine 68.28 equals 0.4. So the rest is now solving simultaneously. So if I do W sine beta divided by cos beta, so that's tan beta, so I don't need to put all the other bits in, you know what I'm doing now. That will be the W sine beta, which is 0.4 times by 0.95 sine 68.28 divided by W cos beta, which is 0.95 cos 68.28. So same sort of thing that happened before. If I do the tan inverse of that, which I'll do now, that gives me 45.118. So three significant figures, 45.1 degrees. So let's highlight that. And then I can substitute that into, get out of the way, an equation to now allow me to work out W. So let's use maybe this equation here and substitute that into there, then to work out W. So W will equal 0.95 cos 68.28 divided by cos beta, so that's cos of 45.1, and I'll use the answer button. So 0.95 cos 68.28 divided by cos answer, and I get an answer to three significant figures, 0.4982205. So three significant figures, 0.498, and remember this was a speed we were working out if we've forgotten what we were doing. So just highlight that so that you can see your final two answers. Right, you should now be able to do exercise 5b on pages 106 to 107. So when we have these multiple collisions, try and use exact values if possible. Yeah, use exact values. Yeah, so don't round in the middle of the calculation, just like anything else that you would do. Your two equations are pretty much the same for most of the questions you're doing, where you've got the two speeds, so u cos alpha equals v cos beta. That's going to be one equation. The other equation is going to do with the coefficient of restitution, which is going to be that speed of rebound, which is going to be always like v sine beta over the speed of approach, which will be u sine alpha. Clear diagrams, very important. So after each section of the question, do a diagram so you can see clearly what's going on, and particularly where you've got like that last example where the walls are at an angle, try and see if you can predict which direction the second collision is going to go in. That's really important. And don't forget your loss of kinetic energy. Yeah, that's basically going to be the kinetic energies before and after, and you just do the largest one minus the smallest one, or you can just do half m v squared minus half m u squared, but for a loss of Ke you'll get a negative answer.